I figured that. Hi, Anaya. Sorry I got in there a little late. Can you hear me? Can you hear me, Anaya?
Yes.
Okay. What's going on now?
Well, it's not a big deal or anything, but so the practice problems that you gave for like the Clausius-Clapeyron equation, I was trying to go in and do some, just for extra practice or whatnot, and
No, it's good. What I'm going to do is I'm going to pull up actually the slideshow I'm going to use today, and I'm going to go to the very bottom of it. Okay, and then we will, it's just got to take a few minutes to load. Okay. All right, that's in there. And let me get the, oh, I don't need the other one. Okay. Vanessa is in here as well. Okay. Now you got to tell me what the parameters of the problem are.
okay, so it was off of so it was, I think it was question 2, and
I don't give me questions. Give me the give me what the problem is. Read the problem to me.
okay, hold on, let me go back here then.
Hi, Vanessa. You in, Vanessa?
Hi, yes, I'm in.
Okay. Anaya has asked a question about the Clausius-Clapeyron, probably the 2-point question. So that's where we're at right now. Okay.
Okay.
Okay, so the question reads, at 50.14 K, a substance has a vapor pressure of 258.9 torr. Calculate its heat of vaporization in kilojoules mole if it has a vapor pressure of 161.2 torr at 277.5 Kelvin.
Okay. All right. So the equation we've got is ln of P2 divided by P1 is equal to negative delta H of vaporization divided by R times 1 divided by T2 minus 1 divided by T1. Okay, are we going with that equation? All right, so plugging the numbers in. I got the ln of, which one do you want to be? We're gonna make the one you told me first, the P1, and the one you told me second, the P2, okay?
Okay.
All right, so my P2 is gonna be 161.2 torr divided by 258.9 0.9 torr. That's equal to negative delta H times
2.314.
1 divided by 277.5 minus 1 divided by 50.14. We good so far?
Yes.
One slight exception. Divided by R.
Yeah.
All right, so I got the ln 161.2 divided by 258. 0.9. This gives me 0.6226 is equal to negative delta H divided by Now I have to change, I have to eventually get delta H in kilojoules. So I'm going to change R to kilojoules right now. So it's not 8.314, it's 8.314 divided by 1,000, which makes it 0.008314 times. I'm sure you read the numbers right.
Yes. I have it here. I have my work here and I have the question pulled up. I've done this problem so many times, it's made my head hurt because the answer that you've given me on the answer sheet didn't match my answer. And I asked a couple of people about it. And like I said, I went to the Success Center and got the question looked at as well because I was confused.
Crap. Thank you. No. Okay. Am I doing something strange for you yet? Am I doing something strange for you yet, Anaya?
No, this is what I got, and I just rounded I just had a 1634 instead of a 33, but you're good.
Okay, that's what I got.
That's not what I got. And can I tell you what I did?
Okay.
Okay, so okay, wait, can you tell me what you did from
Just line. Just tell me the line.
okay, so line 5, well 4 to 5.
4 to 5. I multiply, I'm sorry. I multiplied, or I divided. Actually, I may have gotten it wrong. Okay. I multiplied it and I should have divided it. 0.01633 divided by 0.008314. Straight up. Okay. This answer is wrong. See, so you can get into. Okay. Okay, and does that look
That's
a
what I
little
got.
better? That's what you got?
Yeah, I got 241.08 equals delta H.
All right, close enough. All right.
But yeah,
All right, but the answer is different from that.
yes, on your sheet, and that's why I was confused because I tried to do the vaporization for one as well,
All
and
right.
I
Let's look at the problem first of all, okay, Anaya? And I should
Okay.
have done this in the very beginning. All right. They set up the problem wrong. And I'm saying whoever I grabbed this problem from, set up the problem wrong because it doesn't make sense. Because you've got 50.14 K having a higher pressure than 277 K. Does that make sense to you?
yes.
Okay, so probably if I switch these two numbers.
So I just have a question then. So if this one's wrong, does that mean, or is
Some
set
of
up
the others might be wrong.
okay? Because this is what I kind of use to help me, well, try to help me study, but you know, whatever, I guess.
Is this problem from the quiz today?
No, this problem is from one of the extra homework problems.
Oh, got it.
This should be 0.0. Okay, that's a negative. Okay, I came up with this number, a positive 0.2413, doing it the other way. I don't know. And I don't know how that answer came out to be wrong. But this is the answer I came up with.
That's the answer I got as well, but in joules.
Okay, so what you didn't do is you didn't change this to kilojoules.
No.
That's all.
Yeah, I didn't change it to kilojoules. Yeah, that's what it is. Yeah.
All right. Now you have for delta H, heats of vaporization are always in kilojoules per mole.
I understand. Okay, it's always in kilojoules because I changed it to joules. Okay, that makes a lot more sense. Okay. But
What was the answer?
that I got?
No, what was the answer? What was the correct answer?
37.42 kilojoules per mole.
Okay. Let me look at it. I will look at it in more depth. Okay, Anaya? I thought you were doing a math error and There must be something wrong with the problem itself. That's all I can say. Sorry. I do the best I can at picking these problems out, but sometimes when teachers make things up, they come around. Anybody else have another question? Guys, another question. Somebody said something about the quiz. Hi, Danny. Somebody had a question about the quiz. Okay, I want to go to something. If you guys aren't going to do something here for me, then not going to have any questions, then I'm going to go and actually see the problem that Anaya was talking about. Okay. We are going to go to modules. And for modules, we're going to go here. And oh, crap. It doesn't make sense. The problem itself, I'm looking at problem 2. It doesn't make sense because at a lower temperature, your vapor pressure cannot be higher. Okay. That problem 2 is bad. If you're doing the extra problems, problem 2 is bad because it doesn't make sense. Okay, anybody else have any questions? Any other questions, guys? Can't help you if you don't have questions. Questions about what we did on last week? Nothing? You got nothing for me, huh?
Professor,
Yep, I'm here, Araceli.
do you think we can do another example of the Clausius-Clapeyron equation problem?
No problem. No problem. Okay. Let me go to admit. Which one do you want to do, Araceli?
Number 5.
I can't do number 5.
Uh,
I'm laughing. I'm laughing. Okay, what is the vapor pressure of a substance at 308.1 K? If it has a vapor pressure of 73.15 at 286.6, its heat of vaporization is 25.44. Okay. I think I have everything I need. Hopefully my reputation isn't totally smashed. Okay, so again, the top line is the one that we need to deal with. So I don't know what the pressure is at 308.1, but I do know what it is at 286.6. So I got to plug in my values. My LN of 73.14 divided by X is equal to my delta H. My delta H is 25.44 kilojoules per mole. My R is 8.314 joules times 1 over 286.6 minus okay, can I move this thing down a little bit? I gotta reduce the thing to make it readable. And those are both in K, if I'm not mistaken. Let me make sure I have the numbers right. .301, 8.1, don't know. 73.15 at that temperature. Yes, okay. Now it's just a matter of doing the math. Okay. I can't mess with this part yet. Can't mess with the left side yet. So the first thing I have to do is I have to either change the kilojoules to joules or the joules to kilojoules. This is negative 25440 joules divided by 8.314 joules. This is 0.003489 minus 0.003245. Again, I still can't mess with this part yet.
Quick question.
Yep.
Did you divide your joules? Is that what happened there? You divided
No, I multiplied my joules. No, I didn't divide my kilojoules.
I mean,
What
I'm sorry. I meant your joule values, like two.
I changed my kilojoules into joules from line 2 to 3, and then from line 3 to 4 to get to 4263. I divided the 25,440 joules by 8.314 joules.
Okay, just checking. All right.
Okay, now this is the problem where this is the place where everybody screws up. Algebraically, what you want to do is you want to do this. Right? That's algebraically what you want to do. It is wrong. Do not do it this way. What you have to do is you have to take E raised to the power of the ln of 73.14 divided by x is equal to E raised to the power of a negative 1.040. Did everybody understand that? In order to get rid of logs, you have to do it this way. Now, E raised to the ln power makes this just 73.14 divided by x is equal to, now I'm going to take e to the x, type in negative 1.040, and this ends up being 0.3534. Now it's 73.14 is equal to, now you multiply both sides by x, 0.3534x, divide both sides by and I get 206. 207.0 torr is my answer.
Um,
And you're going to tell me, Anaya, it's a wrong answer, right?
yes, and also when I put 25440 divided by 8.314 in my calculator, I get a different number.
Then that's why my answer is wrong.
Yeah. I wanted to say something, but I didn't want to be wrong because I didn't want to yeah.
I got a negative 1.040.
I got 154.
You got 154?
Yeah.
25440 divided by 8.4.
Okay, take
I-
4263 and multiply it by 0.000244.
426 times what?
0.000244.
Okay.
I got negative 1.040.
That's not what I'm talking about.
Okay.
But it's I don't know. Maybe it's just me. I think it might.
I have a question.
Go ahead.
I think it's the same thing that Anaya is talking about. Where it says negative 25440 joules over 8.314 joules. When I divide that, I got negative.
I'm sorry, wait. I'm sorry. I was trying to get the screen back up. Which line are we talking, Jordan?
It's the third line
Okay.
where you divide the joules.
Okay, 25,440 divided by 8.314. Okay. Thanks, Jordan.
That's what I was talking about.
Okay. There we go. Okay, we good now? Thank you guys for cleaning up. You can see how easy it is to screw up on your math here. And now, are you good with this? My answer look good? Okay. Thank you, somebody, for asking me to do another one. I redeemed myself. Okay. Any questions about chapter 12, intermolecular forces? Because we are going to use those to explain things in this chapter. Questions, guys? Throw them out at me. Okay, another thing, guys, if you do want problems done, I'll be happy to do them in the office hours. I can't really afford to eat up about 10 minutes of time. So what we're going to discuss here, we're going to discuss again how solutions form, degrees of solubility. We're going to come to talk about Henry's law, gases in solution. We're going to get through some concentration terms. And then finally, we're going to deal with the colligative properties, melting point, freezing point, osmotic pressure, and Raoult's law. Now, guys, basically, for definition, so we know what we're talking about, a homogeneous mixture is just two or more pure substances that are mixed such that you can't tell one from the other. In solutions, you get a solute, the stuff being dissolved, dispersed uniformly in the solvent. And what you have to understand, it doesn't really matter. You can have mixtures of solids and solids. If you have something like tin in copper, you have brass. If you have zinc in copper, or it's the other way around. If you have zinc in copper, you have bronze. So these are solutions. These are alloys of metals that are basically solutions, a solid within a solid. We can have a gas with a gas. Look at all this stuff around us. We have nitrogen dissolving oxygen. So we have a gas. Normally speaking, when we're talking solutions, we're going to be talking about a solid being dissolved in a liquid or a liquid being dissolved in another liquid. So Anaya, if I've got 2 grams of sugar in 100 milliliters of water, what is my solute? What is my solvent?
Solute is your sugar, your solvent is your water.
Good enough. Absolutely. Let's see who else is out there. Keanu. Keanu, are you here? Okay. I'm sorry. Valeria. Valeria? Natalie.
Yes.
Thank you, Natalie. We're dealing with 55 milliliters of water and 1.50 grams of sodium chloride. What is the solute? What is the solvent?
The solute is water and the solvent is the other one.
NaCl?
Yes.
Okay, good enough. So basically, to make a solution, as I said in the last chapter, what you got to do is you got to break the intermolecular forces between the solute and the solute, and you got to break them between the solvent and the solvent. You have to break those in order to create a hole in the solvent for the solute to go into. So basically, there are three different energy stages. The first is separating the solute particles. Second stage, we're going to separate the solvent to create holes. Both of those are endothermic. You got to put energy in. Then the third step, we're going to form new interreactions, and those new interactions are going to be between the solute and the solvent. So basically what we're saying is that if a salt dissolves in water, the ion dipole interactions between the ions of the salt and the solvent overcome the lattice energy of the ion for the other ion and one hydrogen bond for the other hydrogen bond. That's what has to happen. So, Gianna,
Yes.
Gianna, thank you. Gianna,
Yeah. Mm,
solid lithium chloride is added to water. It dissolves because the lithium atoms are attracted to the oxygen of the water or the hydrogen atom of the water. Which?
I'm guessing the hydrogen.
Okay, what's the charge on the lithium? Is it positive or negative?
Positive.
What's the charge on the hydrogen?
Positive. Oh, the oxygen's negative, and then okay, lithium is positive, hydrogen is positive. So it need like an opposite charge.
Absolutely. It's
So
attracted to the oxygen atom. Okay? Benita. Benita? Benita, are you there?
I'm here, but my camera has to be off.
Okay, no problem. I'll ask it. I'll ask it to somebody else.
Okay.
Athar.
Yes.
Athar. Now, we said that the lithium was attracted to the oxygen. The chlorine is attracted to the oxygen of water or the hydrogen.
To the oxygen?
All right, again, Athar, chlorine has what charge?
Negative.
Oxygen has what charge?
Oxygen is negative and the hydrogen is positive.
So what is the chlorine attracted to?
To the hydrogen?
Absolutely, absolutely. So what's really happening? Okay, can you see my cursor?
Yes.
If I just have the solvent and the solute before they get mixed and I throw them together, first thing that happens, I need to take energy that's going to separate the solute. I'm going to take more energy that's going to separate the solvent. So now I have separated solvent and separated solute particles. Those are both endothermic. If I then am able to put the solute in between the solvent, that is going to be exothermic. If the overall energy change of the putting the solute in the holes, if that is greater than separating the solute and separating the solvent, I am going to have an exothermic reaction. This is going to be like dissolving NaCl in water. That is an exothermic reaction. If you fill the tube, it will then become hotter. On the other hand, if I have my solute and solvent, again, it's going to take energy to separate my solute. It's going to take energy to separate my solvent. When my solute gets into the holes of the solvent, that portion is going to be exothermic. if putting the solute in the solvent holes is going to be less energetic than separating them, then what's going to happen is that I am going to have an endothermic process. It's going to take energy to do this. Yet, guys, this is something that happens in something like ammonium chloride. And if you've ever been hurt, had a broken arm or something like that, and you go to the hospital and they smash those cold packs, that's what's happening in the cold packs. You have the ammonium chloride separate from the water. When they smack them, it dissolves, it gets colder. That's how those things work. But it doesn't make sense, does it? Manual. Does it make sense that something could be spontaneous when you have to put energy into it?
No.
Okay, it doesn't, you're right. It doesn't make sense that this happens. So there has to be something else out there in the world that's going to overcome this endothermic nature. And the reasoning for this is that there is something else that's involved. Endothermic, exothermic is involved in something called enthalpy. The other thing that gets involved is something called entropy. The tendency for a system to become random. Let me ask you this question. If you arrange cats in 4 nice rows of 5 cats each, and you leave the room, what do you think is going to happen? Are the cats going to stay in the nice, neat rows? They're going to tend to do what cats do, which means they're going to be all over the place. There is a tendency for systems to become random. That is entropy. That is why solutions can absorb heat. What's actually happening is the solution is absorbing heat from the outside water, which makes the water colder. When the water gets colder, that's why we feel it as being a little colder. We're going to get into this in more detail in chapter 18. But sometimes you have to be aware. You have to be aware of what's actually going on. Sometimes when you get this change of heat, it has nothing to do with dissolution or not dissolving. What it has to do is that the chemicals are reacting. So you got to be aware of what you're mixing and what the tendency is to do as to why this heat occurs. Which is why last semester, when we did chemical and physical properties, sometimes you can't use that as an indicator of a chemical change versus a physical change. Okay, we now have to get into solubility. Has anybody ever seen Popeye? Anybody knew who Popeye is?
Are you talking about the cartoon?
Yeah, absolutely.
Yes.
Not the chicken thing, but the cartoon. Gianna, you've seen it, right?
Yes.
What does Popeye say right before he beats the snot out of Brutus?
Oh, I definitely wouldn't remember that. It's been a long time.
I can't takes no more.
Okay.
Every time he does it, right before he eats the spinach and beats the snot out of Brutus, he says, I can't takes no more. That's what a saturated solution is. The solvent holds as much of the solute as is possible at that temperature. Now you have to understand that the dissolved solute is in equilibrium with the solid solute particles. So you're going to have some solid at the bottom Some of it's going to be dissolved and some of it's going to be solid. But there is a constant moving of the solid that's in the crystal form to be dissolved, and some of the dissolved stuff goes back to being a solid. This equilibrium happens. So, I'll ask the question in a second. If we have something that is unsaturated, then we have less than the maximum amount. The solute can have more salt, the solvent can have more solute added to it. So riddle me this, Batman. If I'm looking at two solutions, one has solid in the bottom, one does not. Which one is saturated?
Um,
Come
one
on,
with the
Ethan.
solid on the bottom.
The one with the solid on the bottom, because they're solid on the bottom, the liquid can't take no more. So if you see a solution with solid on the bottom, it's going to be saturated. If you see a solution with no solid on the bottom, it's unsaturated. Yeah, I know. There is that one instance where you're at the perfect conditions and the solvent can't take anymore, but yet there's no more solute there. I'm just saying this as a general rule. If you don't see solid on the bottom, it's unsaturated. If you do, it is saturated. But sometimes we can make a perfect solution. If we take sugar and we keep on dumping sugar into water. Has anybody ever made a mojito?
Yes.
Did you make the simple sugar recipe or did the simple syrup, or did you buy
Yeah,
it?
I made it.
Okay, you kept on putting sugar in there, right?
Yeah, until it was
Wasn't-
really thick.
Till it's real thick. If you keep on going, Jessica, you can make a solution that, literally speaking, looks absolutely clear, but has more solute in there than is possible. It's just that you have made a perfect condition.
Mhm.
Now, if you put something in there, like if you scratch the side, or if you put a string in there, that creates a disturbance. And that disturbance causes all those crystals to come out of solution then. It's how you make rock candy. So let's see. Jessica, while I have you, if, let's see, Jessica, your last name is, yes. By the way, guys, I am taking roll even as we speak. So if you're not answering, you're getting marked absent. Okay, Jessica, at 40 degrees Celsius, I've got 80 grams, the solubility. In other words, the most that water can take of potassium bromide is 80 grams in 100 grams of water. I need you to tell me whether A is saturated or unsaturated, and tell me why. I'm saying, Jessica, that the solution is saturated at 80 grams per 100 grams of water. You have 60 grams in 100 grams of water. Are you saturated or unsaturated?
But don't know.
I don't know. It's a perfectly good answer. We're going to go with Jennifer. You out there, Jennifer? Jennifer? Jenna? Are you out there, Jenna?
Hi.
Hi,
Yeah,
how you-
I would say A is unsaturated
Why?
because you can have up to 80 grams of KVR in 100 and you have only 60.
Okay, look at B. Is B saturated or unsaturated?
I would say B is saturated because they're equal.
Okay,
I'm not confident in that though.
all right. Can you change this ratio so that you have 100 grams of water?
Oh, then yes, it would be saturated then.
Because you would then have 100 grams of KBR in 100 grams of water. Therefore, it's over the saturation limit. You are saturated. Parker. Parker?
Yeah, I'm here.
Okay, Parker, the last one. 25 grams in 50 grams of water. Is it saturated or unsaturated?
It is unsaturated because if
Why?
you made it 100 grams, it would only be 50 grams of KBR.
Finest kind. Good answer. All right. Now, chemists use the axiom like dissolves like. And basically, what this means is that polar solvents tend to dissolve. Polar substances and ionic substances dissolve in polar solvents. Nonpolar dissolve in nonpolar. And basically, this has to do with the intermolecular attractions. Remember, if we have a polar solute, that has dipole-dipole bonds. So we still have to break them, but when we recreate the solvent-solute bonds, it's going to be a dipole with a dipole. That is going to be strong enough to overcome the breaking of the dipole-dipole bonds. On the other hand, if I have a dipole solvent and I have a dispersion, solute, the dispersion forces between the one with just the dispersion and the dispersion of the polar compound is not going to be enough to overcome the breaking of the dispersion bonds. Does this kind of make sense to you guys? Parker, you're the one that's facing me. Does it make sense to you?
Yes, it does.
Glucose, which has hydrogen bonding, is very soluble in water. While something that is very similar in shape to it, cyclohexane, only has dispersion forces, so that is not going to be as soluble as glucose is. As a matter of fact, it's not going to be soluble at all. Something, for those of you that are going into the medical field, you have something called fat-soluble vitamins and you have water-soluble vitamins. Now, when you are looking at a chemical structure, the more carbon and hydrogens that structure has, the more chance you have of it being nonpolar. If it is nonpolar, it is going to dissolve in fats because fats are nonpolar. If, on the other hand, you have a lot of heteroatoms. By heteroatoms, I mean something other than carbon and hydrogen. You are going to have something that is going to be polar in character, and it is going to be more soluble in water. So if I'm looking at the characters of these two, you have vitamin A, which has a whole lot of carbons and hydrogens and only one little OH in it. So vitamin A is going to be soluble in fats. Water, on the other hand, is going to be soluble. Vitamin C is going to be soluble in water because it has a whole lot of heteroatoms in it. Has anybody ever heard of LSD? Am I that old?
Acid.
Thank you very much, Manuel. Have you ever heard about something called flashbacks? When you haven't actually taken the drug, but you go on another trip. Have you heard about that, Manuel?
I have.
What happens there is LSD, like vitamin A, has a whole lot of non-polar character. So LSD will dissolve in your fat tissues. So these things move around in there, and when you get enough of them at one place, it releases it into the water of the cells, which then takes it throughout your body, which gives you a flashback. Now, Manuel, while I have you, look at these two molecules. If I tell you the black balls are carbon and the white ones are hydrogen, red happen to be oxygen, blue is nitrogen. If I am looking at these two molecules, which one would you guess dissolves in fat? Which one is water soluble?
I'm gonna say vitamin E is water soluble and vitamin B6 is fat soluble.
Remember, the more carbon hydrogens that you have, the more of them that you have, the more non-polar character the molecule has.
Okay, so flip them. Okay.
Flip them. Vitamin E has a whole lot of carbons and hydrogens in it. It is essentially non-polar in character. It dissolves in fats, which are non-polar. Vitamin B6 has, relatively speaking, a lot of heteroatoms in there. So it is more polar. It will dissolve in water. Are we good about this, ladies and gentlemen?
I just wanted to ask real quick. So you said the more carbon, the less polar you are?
The more carbon and hydrogens, the less polar the molecule is. Okay, if we're dissolving a solid in a liquid, we don't effectively change the amount of solid that's divided in the liquid by changing the pressure. Essentially, that doesn't happen. Can I ask you a question? Has anybody opened a soda bottle?
Yes.
Okay, this is Natalie.
Yes.
Okay, Natalie, what happens when you twist the cap off of a soda bottle?
The carbon dioxide is released.
Okay, before you opened it, you had a whole lot of pressure in there. So in effect, the greater the pressure, the more of the gas gets dissolved in the liquid. By opening the cap, you've effectively taken that pressure away. You've made it atmospheric pressure, which means the bubbles that were dissolved now come to the surface and you get the foam. In general, as a general rule, the solubility of the gases increases with mass. And the reason for that is the larger molecules have larger dispersion forces. So in general, higher pressure, more gas gets dissolved. Larger the molecule, more gas gets dissolved. So basically, the solubility of a gas in a liquid is directly proportional to its pressure. As with the soda bottle, if I release the pressure, the gas comes out of the solution. If I have a cylinder and I pull the cylinder up, that makes less pressure in there. That means more of the gas is going to come out of solution. On the other hand, if I depress the cylinder, I make a higher pressure. The higher pressure causes more of the gas to be dissolved in the liquid. And they all obey Henry's law, which is a fairly easy formula. The solubility of the gas is equal to Henry's constant times the pressure above the liquid. Simple problem, guys. So if I want to know, and this is basically, guys, how people analyze pollutants in water. What is the partial pressure of dichloroethylene? There's the molecular weight over a sample in a river that contains 0.94 milligrams of dichloroethylene per liter of water. Assume that the Henry's law constant for dichloroethylene is 0.0330 moles per liter atmosphere. Somebody make a suggestion, or I'm going to call on somebody.
I have a question.
Okay, Jordan.
So the 0.94 milligrams, would that be the solubility of the gas?
No,
No.
it's just saying there's 0.94 milligrams in a liter of water.
Okay.
But look, Jordan, what's the label of Henry's law? Read it back to me, the label of it.
Like you want like the equation?
No, I want to know what the label is after the 0.0330.
Oh, moles over liters times atmosphere.
So if I have milligrams, am I going to be able to cancel moles?
No, you have
So
to
what do
change
I
it.
have to do?
Convert it to moles.
First thing I do in this problem is I have milligrams. I got to convert them to moles. So when I do that, I'm going to have the right formula for me to cancel it. So that is the first thing I'm going to do. I'm going to change the milligrams to grams by multiplying by 1 gram over 1,000 milligrams. I am then going to multiply by 1 mole over 96.94 to get the number of moles. That's not a big number, guys. It's going to be a very small number. So I change that. And I end up with 9.7 times 10 to the minus 6 moles per liter. I know what Henry's constant is. I know what my concentration is. All I got to do then is substitute it into the equation. Concentration is equal to Henry's constant times the partial pressure. I put the 9.7 times 10 to the minus 6. I am going to divide that by Henry's constant, and this gives me what the pressure is in atmospheres. I can change it to torr if I want, if the problem asks me for that. Questions? Questions, guys?
Professor, I have a question.
I'm here.
This PowerPoint is on the it's also on modules, right?
It should be, yes.
Okay.
That's where I pulled it from, so I'm fairly sure that it is. Okay, Araceli? Good, Araceli. And I don't want to punish you by asking questions, but I guess I got it. There's a question here. If Henry's law is concentration is equal to K times the partial pressure, is that a direct relationship or is that an indirect relationship?
Direct relationship?
Absolutely. It's direct. If it was indirect, it would be divided by the pressure. So my concentration is directly related to my pressure. So Araceli, with that in mind, what has a higher vapor pressure? A solution that is 4 molar or one that is 2 molar?
2 molar.
You just said
I'm
it's
sorry,
a direct relationship.
4 molar, my bad.
4 molar, because it's a direct relationship. And it makes sense, guys, because if you got more stuff dissolved in there, there's more of a chance that it's going to go up and make a higher pressure. Now, if I'm dealing with solids in liquids, generally speaking, do you get more soluble as you increase the temperature or less? Natalia, you out there?
Can you repeat the question, please?
If you have a solid in liquid, do you generally get more dissolved by increasing the temperature or decreasing the temperature?
Increasing.
Increasing the temperature. That's what this graph is showing you. It's showing you as you get the pressure increased, generally, again, this is a general rule. Generally, you get a higher concentration at higher temperatures. That's partially how you get stuff to dissolve. Increase the temperature. You want more stuff in there? Increase the temperature. The other way to get more stuff in is to agitate it or stir it. On the other hand, if I'm talking about gases, the opposite is true. If I increase the temperature of a gas in a liquid, I decrease the temperature. And that only makes sense because what's happening when I am increasing the temperature, I'm increasing the agitation of everything that's in the solution. If I am increasing the agitation, then that means that I am getting more of the gas to evaporate away, which means it becomes less concentrated. Basically, guys, this is why it becomes an environmental issue around nuclear plants, because what nuclear plants do is they make energy by creating steam. And what they do is they release the steam into the rivers they're located next to. What this does is it increases the temperature of the river water, which depletes the oxygen and kills fish. It also explains if you leave a carbonated beverage out in the hot sun of someplace like Great Salt Lake or the, I've lost my mind. What's the national park that's in California? Death Valley. If you leave a carbonated beverage in Death Valley, chances are you're going to create enough pressure that you're going to mechanically defeat the container and you're going to explode that container. Are we good now?
Yes.
Okay, there are various ways. You define a solution in two ways. You define it by what's in it and how much of it are in it. So we're going to talk right now about various ways of expressing concentrations in solutions. First way is simply mass percent. Mass percent means mass of what you have versus the total mass. What the partial is divided by the whole. So basically, you have 4 grams of a sugar cube and 350 milliliters of water. What is the percent composition by mass of the sugar solution? Density of water at 80 degrees Celsius is 0.975 grams per milliliter. Jennifer.
Yes.
Okay, Jennifer.
Yeah.
All right.
Can you repeat the question, please?
It's sitting right in front of you, Jennifer.
Okay. Let me read it. What is the percent mass by sugar? I don't really know.
Okay, mass percent, Jennifer. Do you know what mass percent is? I just defined it. Mass of your part divided by the total mass of your solution. Do you have the mass of your part? Do you have your mass of your sugar?
The mass of the sugar is 4 grams. So
Alright.
when you calculate the whole mass of the molar mass of sugar and then divided by the grams of the
We don't need the molar mass
No?
because we're doing a mass percentage. Keep everything in grams. The 4 grams is good.
Okay, so 4%.
Nope. You don't know that you have 100 grams of solution. You have milliliters and you have density. Do you have a way of getting grams of your?
Yeah. You can convert 350. Let me see. I could just do it right here.
Jennifer, are you good?
Yes. I'm just trying to figure it out.
No, no problem. Keep on trying to figure it out, all right?
Yeah.
We're gonna go now with Vanessa. Are you there, Vanessa? Remember, guys, if you cut out and I happen to call on you, you get marked absent.
I'm here.
Thank you, Vanessa.
Disculpa,
All right.
está en clase y la llamaron. Está online en clase.
I'm sorry.
Dime.
I'm here.
I understand, Vanessa. Is there something?
Did you call on me to answer a question?
Yes. Do you see the problem before you, Vanessa?
Yes, I do.
Ok, perfecto. Es Germán, pero con H.
Is that somebody is speaking what sounds to be Spanish? Is that coming out of you, Vanessa?
Yes, that is.
All right, sorry. Vanessa, looking at the problem,
Okay.
can you get the mass of water?
The mass of water. One second.
Okay, we're gonna go with Danny. Danny. Are you out there, Danny?
Yes, I'm here.
Okay, Danny. Can you look at the problem and can you tell me how to get the mass of the water?
Yeah, give me 1 second.
Just tell me how to do it, Danny.
Hold on, I gotta click on the board and just figuring this out. Hold on.
Okay, Araceli.
Would we have to divide? Like, for example, if that's the total density, 0.975 divided by 350 milliliters?
If I'm dividing, that would give me a label of grams per milliliter squared. Do you need to divide it?
To get the grams? Or
Natalia, give it a shot.
We need to multiply 0.975 times 350 to find the grams.
Thank
you.
And then do 4 grams divided by 350 times 100 to find the percent composition.
Not quite, Natalia. You forgot one thing.
So you divide the 4 grams of sugar by the total mass of like the combined sugar and like the water.
Exactly.
So 341.25 plus 4 grams, and then multiply that by 100 to get the answer.
Natalia, did you see that?
1
So
point.
I did the
1
problem.
second, Ethan.
I did the problem and I got 341 when I multiplied the 0.975 times 350. So that would be the total mass.
No,
of
it's
the-
no,
right?
you have to include the mass of the sugar as well.
So I need to add 4 more. So it would be
Correct.
340.
That's what I needed you to understand, okay?
Yes.
Again, that problem is solved in the next slide, guys. So basically what you're going to do is you are going to, what in the world did I do here? Oh yeah. I got my mass of my water being 0.975 times 350. I got that being 341.25. So my mass of my mass percent is going to be 4 divided by 4 grams plus 341.25, or it's going to be 1.16%. You're also going to have other values. Instead of percent masses, you're going to have something called parts per million and parts per billion. Now, basically, I'm going to put in a new slide here. Basically, when we have percentage, it is a number divided by 100, correct? Is that correct, guys? Is that what a percentage is?
Yes.
All right. If I want to know what that number is, what the new number is divided by 1 million. If I want to do that, I have 2 ways of doing this. One is I can take, by the way, this is going to be, let me do this for it to make more sense. I can take the number I get, multiply it by 1 million, and divide by 100. And this will give me my X. Let's make this a little better. Does this make sense to you all? Does this make sense?
Yes.
All I'm doing is doing a proportion here. Okay? So in effect, if I'm just doing a proportion, I am taking my number and multiplying it by or is that 100? Yeah. So in order to convert from percentage to parts per million, I have to take whatever percentage I have, divide it by 100, and then multiply it by 10,000, and I will get my parts per million. The other way to think of it is, if I'm going from bottom line, either way you want to look at this, what you have to do is you have to take whatever your percentage is. First of all, you have to convert that to a fragment, a fraction. So to get it to a fraction, you have to divide the percentage number by 100. Then once you get the fraction, the decimal value, you multiply that by 10,000 and you will get the parts per million. I have a 1.16% sugar solution by mass. How many parts per million is this? I can solve it by 2 ways. I can just simply set up the ratio, and this is not really correct. No, this is correct. Sorry. I'm taking the 1.16, dividing it by 100. That's equal to X over 1 million. My parts per million are going to be 11,600. To get parts per billion, instead of multiplying by 10,000, I would multiply by 10 million. Sarah, I see you there now, okay? I need to speak to you after class briefly, okay? Are we okay, guys? Do we understand conversion of percentages to parts per million and parts per billion?
Yes.
So in the example, you multiplied by 1,000,000 and then divided by 100.
Yes. If
So
you
we're
multiply,
if we're given the percentage, we're always gonna do that, right?
exactly,
Okay.
because the percentage is parts per cent or parts per 100. That's what the percentage is. If you have 1.16%, it is the parts that are in 100.
Right, in 100.
So that would be 1.16 divided by 100. You're just trying to ask, what is it in a million?
Okay.
And parts per million and parts per billion are always going to be larger than parts per 100. Another way to express concentration is something called a mole fraction. And a mole fraction is basically the same thing as a mass percent, only instead of using grams, you are using moles. And instead of multiplying by 100, you're leaving it alone. So a mole fraction, the moles of your part divided by the total moles in your solution. Keep in mind, sometimes you're going to need the moles fraction of the solvent, not the solute. Make sure you're using the quantity that you need. A 100 moles is dissolved into 100 grams of pure water. What is the mole fraction of the NaCl? Sarah?
Give me a second.
Okay, Sarah, seconds up. Can you tell me how to do it? I don't necessarily need you to tell me the solution. Just tell me how to do it.
You would divide the 0.100 mole of NaCl by 100.
Is the 100 moles?
Oh, no, you would change the moles to grams first.
Change the grams to moles.
Grams to moles.
All right. That's what the first thing you're going to have to do. You're going to divide the 100 by 1 mole over 18.02. That gives you the moles of H2O. Now what do you do, Sarah? You now have, because you've divided the 100 by 18.02, you now have the moles of H2O. To
You
get
would
the
then-
mole fraction, go ahead.
Yeah, you would then divide the 0.100 moles by that answer.
You have to add the 0.100 moles of the NaCl to the bottom because that is the total moles in the solution. Okay, Sarah?
Okay.
So what I'm going to do, the first step, I'm going to divide the 100 by 18.0. This gives me 5.56. I add that to the 0.100 moles of NaCl. This gives me 0.566 moles total. The mole fraction then is going to be 0.100 divided by the total number of moles. The mole fraction is 0.0178. If I wanted the mole fraction of the water, I would take the moles of the water, the 5.56 moles, divide that by the total, and that number comes out to be 0.982.
Okay.
Are we good, ladies and gentlemen?
Wait, did you give the percentage Of the NaCl? I'm sorry. Where is that?
I didn't give the percentage. I gave the moles of NaCl.
Oh, yeah. I'm sorry. Moles of NaCl.
That was part of the problem, Manuel.
Oh, okay. Sorry.
Nope, no sorry about it. I'm going to skim very much over molarity because basically you should have had molarity back in Chem 1. And molarity is moles of solute divided by liters of solution. Keep in mind, volume is subject to temperature. If you heat water up, it becomes less dense. Therefore, if you have an equation that is temperature dependent, if there's temperature anywhere in the problem, you cannot use molarity because if you change the temperature, you are changing the concentration. Do we need a break, guys? I'm at 5-minute break. This is the question we're going to be looking at when I get back. Okay, guys. Maybe a bad question. That makes it a little better. Ethan,
Yeah.
can you work this problem?
Yeah. Okay, so first you take the 22.8 milliliters of MgCl2, you convert it to liters, and then since you're given the molarity of that MgCl2, so you multiply it by that, and then given the like the equation we're given, you then have to multiply that by 2 to kind of just like account for the fact that like for every mole of MgCl2, you're like also using 2 moles of AgNO3, and then you then just divide that by 0.015 liters of AgNO3 solution to get 0.04 molarity.
Okay. Ethan, perfect. Absolutely perfect. What Ethan did, he saw it was milliliters and he saw that he had a concentration of the magnesium chloride. So he changed the milliliters to liters by multiplying by 1 liter over 1,000 milliliters. And he multiplied that number by the 0.100 molar MgCl. The question said that it completely reacted with all the moles of the AgNO3. So in order for it to do that, what you needed to do was take the moles of the MgCl2 and multiply it by the stoichiometric ratio of 2 moles of AgNO3 to 1 mole of magnesium chloride. This gave you the moles of silver nitrate, which you then divided by the liters of AgNO3, which was 15 milliliters times 1 over 1,000 milliliters.
Yeah, I'm sorry. Could you like go over that whole thing one more time? Again, I'm sorry. I couldn't. Yeah, sorry.
No problem. First step, got to take the milliliters of the magnesium chloride, multiply it by 1 liter, divided by 1,000 milliliters. This gives you 0.0228 liters. You're going to take the 0.0228 liters, multiply it by 0.100. Big M is the same thing as saying moles per liter. Okay? So if I do that, this means I have now gotten 0.00228 moles of MgCl2. My equation says, my balanced equation says there are 2 moles of AgNO3 for every 1 mole of magnesium chloride. So I'm going to take my 0.00228 moles MgCl2 times 2 moles AgNO3 divided by 1 mole MgCl2. You with me so far, Manuel?
Yes.
Okay, I'm going to put this into one line thing. All right. So I do that and I end up with 0.4500456. Now you have to understand from the problem, I know that that number of moles was in 15 milliliters. So I'm going to take my 15 milliliters, again, convert that to,
Put an A. Just wanted to let you know.
yeah, thank you. This makes this 0.0150 liters. Then to get the molarity, I just take the 0.00456 moles, divide that by 0.0150 liters, and this gives me 0.304. Okay, we good, Manuel?
Yep.
Oh, it's nice that I came up with the same answer. Last concentration term. Because we can't use molarity when we have a temperature change, we have to figure out a new concentration term that doesn't depend on liquids. That new term is called molality. It's indicated by a small m. And what molality is moles of solute divided by kilograms of solvent. Because we're dealing with masses and mass is not temperature dependent, this concentration is not temperature dependent. I've got 3 problems here that I'm just going to let go. Except I'm going to work problem 3. If you want to, it's a step-by-step solution. You can see I go step by step in terms of each of these individual problems. It's just extra stuff that you can look over as a template to help solve it for other things. All right, I want the molality of a 3.62% by mass. If that is the case, let me see what the original problem was. Okay, if it is 3.62%, then it's 3.62 divided by 100. Are you seeing where I got that? Remember, mass percents are mass of your part divided by mass of your whole. If it is mass of your part divided by mass of the whole, then the amount of the sodium hypochlorite that I have is 3.62. That's in 100 grams of solution. But in order to have 100 grams of solution, I have to subtract 100 and 3.62 to get my grams of water. Now I want molality, which means that is moles of my solute, moles of my sodium hypochlorite divided by kilograms of solvent. So for this, I'm going to, there's an error here I can see already. For this, I am going to find my moles of my solute, which are going to be 3.62 divided by the molecular weight of sodium hypochlorite, which gives me 0.0486 moles of sodium hypochlorite. I take my grams of water, multiply it by 1 kilogram over 1,000 grams. I get 0.09638 kilograms of water. For my molality, I take my moles of sodium hypochlorite divided by my kilograms of water. And this is going to give me a slightly different number. That gives me a molality of 0.504. If I want the mole fraction, I have to get the moles of my water, which I take the 96.38 and divide it by 18. That gives me 5.35. If I want the mole fraction, that is the moles of the sodium hypochlorite divided by moles of sodium hypochlorite plus the moles of water. I do that math out, I get a mole fraction of 0.0833. For the most part, guys, this is dimensional analysis. Any questions?
Professor, I have a quick question.
I'm here, Natalie.
Dividing the 0.486 divided by 0.486 in the last problem, the moles Na,
plus the moles of water.
but you have to divide the NaOCl divided by NaOCl plus the moles of water. Wouldn't that be 1 plus 5.35?
No, it's the moles. It's 0.486. Ah, no, there is an error there, and this is what it should be.
But regarding, wouldn't that 0.0486 divided by 0.0486 equal to 1?
No. No, because it's divided by 0.0486 plus 5.35.
I don't get it.
Let me redraw it for you, okay?
Oh, okay.
You understanding now?
Okay, yep, I got it.
Okay, that's sometimes the visual is worth more than my sitting here and talking about it.
That makes sense. Thank you.
Any question about conversion of one of these concentration terms to another? Talk to me now, guys. Because if not, I'm going to assume you're knowing it.
No question.
I'm hearing crickets. Keanu, where were you earlier?
I had to get up and go away for a moment. Sorry.
No, sorry about it. Let's understand from now on, if you go away, that means you're marked absent for the day. Valeria, where were you earlier? Valeria, are you there?
Yeah, I'm here. I was printing my slides and the printer got stuck. So I could hear, but I couldn't come back into the room fast enough.
Okay. Again, make that understanding. Let me see. Danny, I got already. Samantha, you out there?
Yeah.
Thank you. Jana.
I'm here.
Leonardo?
Here.
Leonardo, make
Here.
sure that you talk to me about the lab. Zachary. Zachary. Raylina,
Here.
Rhea,
Here.
Emily,
Here.
Delexis. Okay. Ladies and gentlemen, while I have your attention and while everybody's not rocketing to get out of here, Sarah, I need to talk to you. Leonardo, Angus Ferguson, if you're there, Jessica Kramer, Alec McGregor, Catherine Nickens, and Jessica Solea. If you are there, I need to speak to you after class regarding the laboratory.
Sounds good.
Okay. Last thing we have to talk about are something called colligative properties. And colligative properties are something that depends upon the quantity of the stuff, not the type of the stuff. It doesn't matter what it is, we're talking about particles. The colligative properties are dependent upon particles of substances, not on what it is. Among colligative properties are vapor pressure lowering, Raoult's law, boiling point elevation, melting point depression, and osmotic pressure. So, when you dissolve something in a liquid, what happens is its vapor pressure decreases, because what the solvent is doing is it's dissolving your solute. So if it is dissolving the solute, there is an attraction from the solute to the solvent. There are intermolecular forces there. So therefore, as you add more of the solute in there, you get more of the solvent that's bound up by this solute-solvent intermolecular interaction. And because of that, vapor pressure is dependent on concentration. Now, I get people that confuse this with Henry's law all the time. Henry's law involves a gas being dissolved in a liquid. Raoult's law involves a liquid that is dissolving a solid. Its vapor pressure gets lowered because it is dissolved by that solute. And Raoult's law states the new pressure is equal to the mole fraction of the solvent times the original vapor pressure. X is the mole fraction of the solvent. X should be the larger part of a half. In other words, the solvent is usually more than half of the solution. So it should be a relatively large number. Remember, you want the mole fraction of the solvent. Glycerin, a non-volatile, non-electrolyte with a density of 1.26 grams per milliliter at 25 degrees Celsius. I got all too many wires here. Thank you. So we got a density of 1.26 grams per milliliter at 25. Calculate the vapor pressure at 25 C of a solution made by adding 50 milliliters of glycerin to 500 milliliters of water. The vapor pressure of pure water is 23.8 torr at 25 degrees Celsius. So we know what the original vapor pressure is of pure water. That's what P superscript 0 is. That's a vapor pressure of the pure substance. I need to find the mole fraction of the water in the mixture of water and glycerin to multiply that by the vapor pressure of the pure water to get the new pressure. Mole fractions are less than 1. Who wants a gimme question? Gimme question, Jana. Jana, you there?
Are you saying Jenna or Jana?
Jana. Jana. J-A. Jana.
I'm here.
Thank you, Jana. This is a gimme question. You have your picture out there, Jana.
Okay.
You video up?
Yes, I am.
Okay. So if the mole fraction is less than 1, should the new pressure be more or less than the pressure of the pure liquid?
It should be more.
The mole fraction is less than 1. I'm multiplying the mole fraction by the original pressure, the pressure of the pure liquid. So the question is, should the pressure of the solution be more or less than the pressure of the pure liquid if the mole fraction is less than 1?
No, it should be less.
It should be less because I'm multiplying. X is going to be less than 1, so I'm multiplying the pure pressure by something less than 1. Regular PA is going to be smaller than P superscript 0. So what we have here is we need to find the mole fraction. We know the formula of glycerin. And we know that there are 50 milliliters and the density of glycerin is 1.26. Can we get the mass of glycerin?
Yes.
Thank you very much. How do we get the mass of glycerin?
We're gonna do dimensional and wait, is the density for, yeah, that was the density for glycerin, correct?
Yes, it
Yeah, we're gonna
is.
go from 50 milliliters of glycerin and then we're gonna convert it to grams by multiplying 50 milliliters times 1.26. That gives us grams.
We
And then
got,
we're gonna go
we got 63 grams of glycerin. Now
63,
continue on, Manuel. You're doing good.
63 grams of glycerin.
Remember, we want the mole fraction.
And then from grams, we need to find out the molar mass for glycerin, which
48 and 8 is 56, and 56 and 36 is somewhere around 92.
okay, I'm gonna trust you on that.
Don't ever trust me on that.
Okay, do you want me to do the hold on.
Actually, it's 92.1.
92.1? Okay.
So basically, I've got 63.0 grams of glycerin divided by 92.1. I got 0.684 moles of glycerin. The problem told you I have 500 milliliters of water.
So
Guys,
then,
generally speaking, if I give you a volume of water, just assume that the density of water is 1 gram per milliliter.
okay.
So
And then we're
remember,
gonna-
what am I going to do now, Manuel?
Oh, we're gonna do the same thing, but with water. So 50 milliliters. and then-
500.
Or 500, I'm sorry, 500 milliliters, which you said is, the density is 1 gram.
Yes.
So then that's 500 grams, correct? Or
Yes.
no, okay, yeah, 500 grams. And then from there, we're gonna do we're gonna add 500 grams plus 0.68 grams.
No, 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 the 0.68's moles.
Oh, moles. I'm sorry. Yeah. I'm sorry. Oh, wait, let me go back. So then we're gonna convert the grams of water into moles of water, correct?
Exactly.
So 500 grams divided by 18.02.
That gives you 27.7.
Okay.
Now,
27.
remember, when we are doing Raoult's law, we want the mole fraction of the solvent. So what we are going to do is we're going to take the solvent moles divided by the solvent plus the solute. I'm going to take 27.7. I'm going to divide that by 27.7 plus 0.684. I get that mole fraction. It's going to be 0.975. Manuel, finish it up. Feel good about finishing the problem up.
I'm not gonna lie, I kind of wait. So you said 0.975?
Yeah, that's the mole fraction.
Okay, so then it's 0.68 divided by 0.975, correct?
No. X is the mole fraction of the solvent. Okay?
Okay.
We just got that by taking the moles of the solvent, the 27.7, the moles of the water, divided that by the moles of water plus the moles of the solute, which was the glycerin. This gave us 0.975 moles, a mole fraction. Then Raoult's law says the new pressure is going to be the mole fraction of the solvent times the original pressure of water, which is 23.8. I do that math out. My new pressure is going to be 23.2 torr.
23.2?
23.2.
Okay, yep.
Questions, ladies and gentlemen?
I have a question.
I'm here.
I just wanted to ask about where we exactly got the torr measurement from.
Okay, the 23.8?
Yes,
Jenna?
sir.
The 23.8 came from the problem. It said the vapor pressure of water, pure water, at 25 is 23.8 torr.
Okay, thank you.
That makes sense?
Yes, it does.
Okay. I was going to do something and second problem. Vapor pressure of pure water at 110 C is 1070 torr. A solution of ethylene glycol and water has a vapor pressure of 1 atmosphere at 110. Assuming that Raoult's law is obeyed, what is the mole fraction of the ethylene glycol in the solution? Samantha.
Yeah.
All right. We have Raoult's law, which is new pressure is equal to the mole fraction divided by the original pressure of the pure solvent. Do I have the vapor pressure of pure water in there, Samantha?
Yeah.
That is?
110.
Look again.
Oh, 1070.
1070. All right. Do I have the vapor pressure after the ethylene glycol has been added?
1 atmosphere.
1 atmosphere. Okay. So what am I going to have to do?
Convert it to torr, or the other
Convert
way
it to
around.
torr.
Convert it to torr.
So basically, I'm going to take my 1 atmosphere. That is the pressure after the ethylene glycol has been added. 1 atmosphere is 760. That goes on the left side. That's the new pressure. I don't know what the mole fraction is, but the pressure of the pure water is 1070. So I divide the 760 by 1070, I get a mole fraction of 0.710. But I gotta look at the question. The question asks, what is the mole fraction of the ethylene glycol? What is X at this point? What's it the mole fraction of? Take a guess, Sam. Is it the ethylene glycol or is it the water?
I don't know.
Remember, X is the mole fraction of the solvent. So what is the 0.7?
Is it the water?
It's the water. It wants the mole fraction of the ethylene glycol. You have to understand that when you add all of the fractions up, it's going to be 1. So in order to get the mole fraction of the ethylene glycol, we're going to take 1 and subtract the mole fraction of the water. The mole fraction of the ethylene glycol is 0.290. Questions, ladies and gentlemen?
I have a question. Is
I'm
that a general rule that we should always remember that all the fractions will always equal 1, so 1 should always be part of the equation?
Sarah, it depends upon the question that's asked.
Okay.
If you add up all the mole fractions of a solution, all the mole fractions will add up to be equal to 1.
Okay. That was what I was asking. I just didn't word it right.
Sometimes I try and bluster my way through an answer. Okay.
Yeah, thank you.
Okay. Leonardo, have I bothered you yet today?
No.
Should 4 molar solution of the NaCl have a higher or lower pressure than a 2 molar solution of NaCl in water? Which
It would have a
one
lower
should
pressure?
have, which one should the water have a lower vapor pressure? A 4 molar solution or a 2 molar solution?
Would it be the 4 molar solution?
I'm sorry, Leonardo, I just lost my thought. Did I ask you which one would have a lower pressure?
Yeah.
The 4 molar will. Do you know why, Leonardo? Or was that a lucky guess?
It was just from like the definition earlier you gave us about colligative properties.
Absolutely. 4 molar solution, to explain it in depth. A 4 molar solution has a higher mole fraction of NaCl than a 2 molar solution does. Does that make sense, Leonardo?
Yeah.
If the NaCl has a higher mole fraction in 4 molar, that means that the water mole fraction is smaller. If the water mole fraction is smaller, then the pressure will be smaller. Does that make sense?
Yeah.
All right, the other reason is the exact thing we explained. If you put a solute into a solvent, part of the solvent's duties are going to be to keep that solute dissolved. So it has intermolecular forces with the solute, therefore its pressure is going to be less. I'm going to skip this because I got 18 minutes left. Somebody remind me I have to go through boiling and freezing points. I'm going to skip to osmosis because that's one thing as opposed to two. Again, there are 4 colligative properties. We just dealt with vapor pressure lowering. Now we're going to deal with something called osmotic pressure. If you have a semi-permeable membrane, what this does is it allows some of the molecules to go through, holds back others. In biological systems, cell membranes allow water to pass through, but solutes are not free to do that. So what happens? Eventually, you want to make both sides of the equation equal. So if I have a concentrated solution and I have a dilute solution, I want to make both sides the same concentration. So what is going to happen is some of the liquid from the dilute side is going to go into the side that's more concentrated until we get both sides to be the same concentration. Well, what happens is I got more liquid on the left side than I do the right. That has created a pressure difference. The act of more liquid moving from right to left increases the pressure. That pressure is called osmotic pressure. Questions on the whole process about osmosis? So what happens? We get liquid moving to the more concentrated liquid. That causes a movement, a liquid pressure that increases as we are looking at the concentrated side. That formula, osmotic pressure, is designated as pi. Pi is equal to moles divided by volume, which is molarity. Pi is equal to molarity times R times T. R is equal to 0.08206 because, look, the volume is going to be in liters. So the R, you want the R to be in liters. Temperature is Kelvin, R has to be in Kelvin. We're dividing by, or we're multiplying by moles, so R has to divide by moles. So the R value, and what we're left over is going to be pressure in atmospheres. So that's why R in this instance is equal to 0.08206. If the pressure on both sides of the membrane are the same, it's called isotonic. There's no movement of liquid from one side to the other. But again, as you guys that are going into medicine need to be aware, okay, if the concentration outside the cell is greater than inside the cell, what happens is the liquid that's inside the cell moves out of the cell, and basically you lose all the water in the cell and crenation occurs. In other words, you destroy the cell because there's no water in the cell. If the concentration outside the cell is greater than inside the cell, that is called something being hypertonic and results in crenation or a killing of the cell because all the water has left. You can also have the opposite effect. If the concentration, let me go back here for a second. Think about drinking ocean water, guys. If you are drinking ocean water, isn't the concentration outside the cell of salt greater than the concentration inside the cell? If that's the case, then what's happening is the water from all your cells is going out to try and dilute the ocean water. So this is why you do not want to drink ocean water. Does that make sense, guys? On the other hand, if we have a low concentration outside the cell, what is going to happen is the cell is going to continually absorb water until it breaks the cell membrane. And what happens is you get hemolysis occurring. I have 125 milligrams of an alkaline earth chloride. It's dissolved in enough water to make 50 milliliters of solution at 298 Celsius. It has an osmotic pressure of 1.16 atmospheres. Identify the alkaline earth metal. Okay, we know what the osmotic pressure is. We have the temperature, we know R. So the osmotic pressure divided by RT is going to be equal to my molarity. I take my 1.16 atmospheres divided by R, divided by the temperature in Kelvin. My molarity is 0.0474 moles per liter. Now, I'm going to get into Hoffman's law on Thursday. But basically, remember, colligative properties have to do with particles, number of particles. So if I have an alkaline earth metal, alkaline earths have a +2 charge. So my alkaline earth chloride is going to be XCl2. I have 3 particles for every molecule. So since there are 3 particles for every molecule, I have to divide the molarity by 3. So I now have my molarity of my magnesium chloride as 0.0158 moles per liter. The 0.0474 moles per liter was the molarity of the moles of X plus my moles of Cl. So I had to divide that number of moles by 3 to get the molarity of my XCl solution. So that's where I came up with the molarity being that. Now, the question said there were 50 milliliters. So I'm going to change my 50 milliliters to 0.050 liters, multiply it by my new concentration. I have 0.00079 moles. To find out what the molar mass is grams divided by molar mass equal moles, or grams divided by moles is equal to my molar mass. So I take my grams divided by my moles, I get 158. Contribution to the molar mass by chlorine is 35.5 plus 35.5 or 71. So my molar mass minus 71 gives me 87. I look to the periodic chart and find out that that is strontium. Hard question. Hard question. Rhea, do you feel up to it?
Yeah.
All right, Rhea. Remember I said colligative properties are dependent upon number of particles. When I put an ionic salt into solution, it breaks up into its ions. Ions are considered particles. Okay?
Okay.
I set up a tube with a semi-permeable membrane. One side of the tube is water, and on the other side is a mixture of lead nitrate and barium chloride. Will there be an increase in osmotic pressure after the reaction proceeds? Remember, if it's a solid, it is not in solution. So Rhea, how many particles does the lead nitrate contribute? How many leads are there in that salt? How many lead atoms?
1.
How many NO3s?
2.
2. So lead nitrate gives you 3 particles. We good?
Mm-hmm.
Barium chloride. How many barium atoms?
1.
How many chloride ions are produced?
2.
So I've got 3 particles from the lead nitrate, 3 particles from the barium chloride. All right? So I've got 6 particles on the left. Now, the lead chloride, does that deliver any ions into solution?
No.
No, it's a solid. How about my barium nitrate? How many does that deliver? How many barium ions in every barium nitrate?
1.
How many nitrates?
2.
So essentially, I'm going from 6 particles to 3. Am I decreasing or increasing my molarity?
Increasing?
I'm going from 6 particles to 3.
Oh, decreasing.
I'm decreasing the molarity. So if I am decreasing the molarity, here is my equation. Pi is equal to molarity times RT. Pi is the osmotic pressure. if I am decreasing my molarity, is the osmotic pressure going up or is it going down?
It's going down.
Down. My molarity is going down. It has a direct relationship to my osmotic pressure. So my osmotic pressure is also going down. Thank you, Rhea. I think it bothered him here. Cherie, are you here, Cherie? Cherie. Who wants to end this up today, guys? Got 3 minutes left. One slide I'm going to go through. Who wants to end it quickly? Ethan.
Okay. So I think solution B would have the greater osmotic pressure.
Because you're looking to delete. 10% is greater concentration than 5. You're looking to I'm sorry, other way around, Ethan. 10% is a greater concentration. So you're going to get a flow of liquid from the lower concentration to the bigger concentration. So solution A has a greater osmotic pressure.
Okay.
So from that, it flows from B into A. The level of B will be lower.
Yeah. Okay.
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 Guys, this is close enough. Question, Ethan?
No.
I'll be honest with you guys. Even though they're the simplest equations, this is the area that people have the most trouble with when I'm doing my test. You have a real hard time working your way around the colligative properties. And I think it has a lot to do with the fact that there's a lot of equations and it gets to be confusing. You don't know which equation to use. I'm just giving you a heads up on that. Do you all have any questions for me?
No.
Having said that, guys, I'm here. I will be again available at 9:45 on Thursday for the office hours, and class will begin at 10:15. If you don't have a problem, guys, I will see you on Thursday then.
See. Bye.
Thank you.
You're welcome. Thank you.
Have a good one.
You have a good week.
Did
Some
you
of you-
want us to stay for the lab information?
Yeah, thank you. Yes. Okay, Jessica.
Yeah.
All right, you weren't in lab today, which is, I mean, you're not required to be there. Were you there on either day last week?
Yeah, I was there on Thursday last week,
Okay, so,
and I took the syllabus quiz as well.
okay, I didn't see that. I was looking at the things. Okay, good enough. Fair enough. You're absolutely right. I should have looked there instead.
Okay.
Sarah, don't worry. You're in the lab, okay? Sarah,
Okay.
Sarah, same thing. Did you do the syllabus quiz?
Yes.
Okay. Let's see. Is Leonardo there?
Yeah, I'm here.
Did you do the syllabus quiz?
Yeah.
All right. I need to have something that says that you were in the lab. Angus is not here. Alec McGregor is not here. Catherine or Jessica. Neither one of you are there either, correct? What it saves me is it saves me from emailing you and having you to email me back that yes, you were in the class. That's all.
Okay.
That's it. So good enough. All right. Take care, guys. I will see you.
Thursday.
I will see you on Thursday.
Thank you. Have a good
Professor, I have
day.
a question real quick.
I'm here, Leonardo.
So you said for the in-person today is going to be a Zoom meeting, right? For the graphing?
No. I'm sorry. Whoa. Leonardo. First of all, Leonardo, I'm an idiot. I know you were there last week. I remember you're the only guy in the class. So yes. Now, I'm sorry. Ask your question again, Leonardo.
You said today we're going to have a Zoom meeting for the graphing
No,
instead of
did
the
I?
in-person. Yeah, that's what you said.
Okay, good. That means I don't have to drive out there. Okay.
Okay.
That sounds fine to me. 2 o'clock. 2 o'clock will be there, right?
Okay, I'll see you at 2 o'clock.
Thank
Yeah.
you for reminding me.
Okay.
Professor, I have a question about that lab because I'm in the face-to-face lab. I think I emailed you about this today. My sister's my sister's graduation, and I might be leaving early.
Natalia, trust me.
Yes.
I've been through 3 graduations in my life. They're boring as snot. I'm saving you. I am saving you from having to go through this, service.
Yeah, I know.
You have to sit through boring speeches. Then you have to sit through all these people. What university is it, Natalia?
It's high school, so it's almost 700 people.
You see, it's going to take 700 people. You're going to be bored as snot. Obviously, Natalia, I'm very glad Leonardo brought that up to me. I was Zoom meeting it, and you can watch it. If nothing else, do you know how to graph using Excel?
Not much. I barely use Excel.
All right. It's not that hard. It's a very simple process. I have a video that I'm going to be showing, and then I'm going to go through it myself. Okay. But it will be in the Zoom meeting.
Okay, perfect. Yeah, I will attend for the first part. It's just that her graduation starts at 4, so I might be leaving like 3:30 something.
Oh, dear God, I'm not going to be that long. Dear God.
Oh, really? It's just, yeah, I wasn't sure because does the class start at 2 p.m. or 2:30?
2.
2? Okay, because I was getting that confused. Okay.
I'm like 90% sure it begins at 2.
Okay. Okay, so
you have made me doubt myself now.
No, I've been thinking about it since yesterday. I didn't know if it was 2 or 2:30.
I'm telling you. I'm telling you. I'm trying to save you from being bored out of your mind.
I know.
Younger sister?
Yes.
I suppose she attended yours, so you have to attend hers.
I didn't have a graduation because I graduated last year, so it was a virtual one. Yeah.
Then you have no experience at all.
No.
Yes, you need to be punished. You need to be punished. Go to the graduation.
I will. Okay, thank you.
You're welcome. Have a good day.
Professor, I have a question.
Yes, Satchel.
Yes, just making sure when you said, I think it was Shari or something, you weren't calling my name, right?
I've already got you marked absent because you weren't there when I called your name to answer a question.
Because there was at some point, it was about like maybe 30 minutes ago, I had to pick up a phone call and I had to put my laptop aside and take that, and then I came right back.
All right. I'm sorry. First of all, am I saying your name correctly?
It's Sachari.
Sachari. So
that's why I was wondering, maybe like you called it, but you didn't say it right. So I didn't know if you were calling me.
Okay. All right. I got you. I have you marked present for today. Okay.
Okay. Thank you, Professor.
Just realize that if I do call on you and you're not present, You get marked absent.
Yes, I know, Professor.
Okay, and just make sure that you correct me in the end, all right?
Yes, yes. Okay, no problem. I'll see you at 2.
See you at 2.
Bye.
Did you still need to speak with me, Professor?
Sorry, Sarah. I didn't realize you were still on here.
It's okay. Did you need to still speak with me, or was it be just?
No. Did you complete the syllabus lesson?
Yeah, I did. I just have a quick question. So, am I required to go to the Zoom meetings Tuesdays
No.
and Thursdays?
No.
No.
I cannot require that because the class was listed as an online class. The difference is if you see something that says live online, that means you are required to do whatever attendance the professor demands. And being as it's an online class, I can't demand that you attend. Having said that, there is a big correlation between those that attend and a better grade.
Okay. No, I was just wondering because I missed today because I was just kind of confused about that. So I didn't know if it like counted towards my grade. But no, I'll be there. I was just confused.
Today was a worthless example.
Okay.
Mainly because a lot of the people worked ahead. There was an assignment that was listed as being due May 23rd, and there was nothing in it. That's because I have to create dummy assignments so that I can take all of your individual grades, add them up, and put it into this dummy assignment so that when a grade gets dropped, the same grade, all of the grades are equal that they're considering. Does that make sense, Sarah?
Yeah, no, I understand. Okay, that's all I had. All
Okay.
right, thank
No problem.
you. Bye.
Bye.